In today's video, we'll be talking about work. After watching this video, you should be able to understand what work is and the units of work, and then also be able to use the work formula to calculate the total amount of work completed. So let's get right to it. Previously, when we had talked about motion, we had been using things like kinematic equations, or we've been talking about momentum, kind of a different approach to kind of discussing this idea of work. Or I'm sorry, to discuss this different idea of motion. Now we're going to take motion on from the standpoint of how much work does it take to put an object into motion and the amount of energy required to do that. Okay, and so we'll be looking at the effect that work has upon the energy of an object or a system of objects. And so by using that information, by taking the amount of energy used by an object, we can then obtain things like velocity, height, and all that good stuff. So we're still kind of using the same ideas, but now we're kind of just taking a different approach, a different perspective to what we have been doing previously. So you may be asking yourself, I've heard of work before, you know, I've gone to work, I had a job, or I have to do work sometimes like yard work. How is work different in physics? Well, work is basically a force that acts upon an object and causes a displacement of that object. And there's three key ingredients to doing work. One, you need a force. Without a force, you won't have work. The second is you need a displacement. So there has to be some motion of the object in some direction, either up, down, left, right, whatever. There has to be some displacement. And there has to be a cause, okay, so that the force basically causes that displacement. Okay, so that's going to be a key thing, the cause piece, understanding that force causes that displacement. All right, so I'll explain that in just a second when we start talking about the formula, which is my next slide. So let's take a look-see at it. Work equals force times distance. Now this is going to be an important formula for a while here. Okay, so this is one worth writing down. All right, so work equals force times distance, and then here's this cosine theta. Okay, this is the cause piece, the cosine theta. And I'll get into that in just a second. I'm going to just draw you guys a picture here in just a second. The units of work will be measured in joules, and a joule is a Newton meter, okay? And sometimes you'll see work as like the delta E, or the amount of energy that has gone into an object, because work is basically a form of energy. Now, we had said before that there's basically three pieces to work, and I'm going to draw a box here, and here's like the ground, okay? The first, to make this box, or have this box undergo work, we have to apply a force to it. Okay, there has to be a force applied to it. Then basically that force has to be strong enough to cause some sort of displacement. You know, I'll call that X, some sort of displacement. So you have the force, we have a displacement, and this force has to be causing that displacement, which is the cosine theta. And basically that if the force and the displacement are in the same plane, that they're lined up together, and there's no change in the angle between the force and the displacement, cosine theta would be 0. Okay, and if you take the cosine of 0 degrees, that becomes 1. So sometimes you won't even see this piece in the formula, but it's not really true. And the reason why it's not really true is because if you apply like a force at a 90-degree angle, if I apply it straight down, could I possibly make this box move to the right or the left? And the answer is no, right? And the way that cosine theta comes in to explain that is if you take the cosine of 90 degrees, throw it in your calculator if you want, it's 0. Okay, and if you have 0 times anything, it's 0. You cannot, you know, provide the work or the energy necessary to move that box in the right or left direction if you're applying a force at a 90-degree angle to the displacement. Okay, so here's the force, here's the displacement. Okay, and this will make more sense as we go through examples, but this is just kind of what I was talking about in the previous slide. So let's do some examples of what work is or is not. Okay, so here we go. It says a teacher applies a force to a wall and becomes exhausted. Is that work or not? Okay, and sometimes you need to draw a picture to do this. Okay, so like here's a picture of a teacher or some person applying a force to a wall. Okay, and they push and push and push and they eventually get tired. Was work done? There certainly was a force, right? But was there a displacement? And unless this teacher is like, I don't know, the Hulk or whatever, there is no displacement, and so anything times 0 is 0. So there was no work done, even though it was extremely exhausting for the teacher and he's probably going to go home, or she's going to go home sore and tired. There was actually no work done in terms of physics as a standpoint from that, okay? A book falls off a table and free falls to the ground. So again, I'm just going to draw a real quick picture here. Here's a table. Here's the book, and it's falling to the ground. Now, is there a force acting upon the book to make it fall to the ground? The answer is yes. That is the force of gravity, F sub g. Does it move some distance or some displacement? Does the book have some displacement? The answer is yes. Whatever the distance is from the tabletop to the floor, right? That's its displacement. And is the force in the same direction as the displacement? The answer is yes. So work was done. Work equals yes. Okay, but we definitely had some work here. Now this one's tricky, so definitely think about this one. A waiter carries a tray full of meals above his head by one arm straight across the room at a constant speed. Okay, so here it is, this waiter. I am far from a good artist, but we'll say there's a glass of water on it. He's carrying this tray, and it's moving across the room in this direction. Now, is there a force upon this tray? There is. There's the force of gravity, right? And it's moving at a constant speed. So there is actually no horizontal force per se to cause this thing to move. It's moving at a constant speed. The displacement is in the right direction, but notice, so I'll label that X, the direction to the right. But notice this is a 90-degree angle, okay, between the force of gravity and the displacement. And so we would have a cosine of 90 degrees. And if you remember, I said the cosine of 90 degrees is 0. So anything times 0 is 0. So this actually is not work. Okay, it's a very tricky question, but because basically he's moving at a constant speed and he's not taking the tray and like moving it up and down vertically, there is no work happening here. Basically, if we go back in time, whenever he lifted the tray up off the counter or wherever he got it, that was work, yes. But if we just take a look at this sentence here, a waiter carries a tray full of meals above his head with a straight arm across the room at a constant speed. No work was done, actually, believe it or not, in terms of physics. Okay. So let's take a little deeper look at the work equation. This theta piece, I think, is probably the most confusing part of the equation. And again, it is associated with the amount of force that causes the displacement. Okay, so if you're, I'll just draw a little box here. If you're moving this box to the right and you're applying a force at an angle, we need to basically figure out the angle between the force and the displacement direction. That's theta. Because if you're applying a force at this angle, we know when we break this force into vectors, not all of it is going in the x direction. Some of it's going in the y direction, right? Which does not aid, if you will, in the movement of the box. So this is kind of a place where sometimes people get tricked, is like, if the force on this little car here is being applied at an angle, but it's also moving up a ramp at the same angle that the displacement and the force are in the same line, theta still is 0 degrees. Even though people may want to measure theta from the ground to this displacement angle, that's not the case. You have to look, and this is something I will put stars next to, because this is what's important. The angle of theta is the angle between the force and the displacement vector. So the angle between the force and the displacement vector. Now you notice here the force and the displacement vector, they have the same exact angle, right? And so theta would be, again, 0. But if you can see this box up here, the angle between the force and if this is the displacement vector, that certainly isn't 0. They both aren't pointing in the same direction. And that's where this theta piece comes in. And through practice, this won't be such a big deal. But I'm just trying to really hammer it home here so that you don't make careless mistakes on homework assignments or that type of thing. Okay, so believe it or not, you can actually have negative work. And you might say, what? How can you have negative work? Well, basically, when a force acts upon a moving object to hinder a displacement, it can cause negative work. And you might say, what's an example of this? Well, a good example would be something called friction. Okay, friction hinders the movement of an object. It slows the displacement down, right? And so if you calculate the work done by friction, typically it's going to be a force that is in the direct opposite direction of the displacement vector. Okay, so again, maybe a picture would be worth 1,000 words here. Here's the displacement vector going to the right, and the force of friction, which I'll just write F sub F, the force of friction is going the opposite direction, right? It's going to oppose the motion of this box. The angle here is not 0, instead it's 180 degrees. Okay, that's theta. And if you take the cosine of 180 in your calculator, you'll get -1. Okay, and so you actually do get a negative work value. Basically, it's energy that's lost, if you will, due to friction. Okay, and so negative work is certainly okay. You can have that happen. So don't freak out if you see negative work. You probably did something right, actually. All right. Let's take a look at an example problem just to kind of get you an idea of what you might be expected to do. Okay, this one, basically the trickiest piece here is that we have this free body diagram where you have a normal force of 20 newtons up and a force of gravity of 20 newtons down, and then you have an applied force of 10 newtons. Again, you're looking for the net force, and you'll notice the normal force and the gravitational force, they balance each other out, right? They're going in opposite directions and they're equal in terms of their magnitude, and so that they don't actually apply here in the work equation, which I'm going to write down right now. Work equals force times distance times the cosine of theta. Okay, so what is the net force here? Well, the net force is this guy right here, 10 newtons. Okay, so we have 10 newtons times, let's see here, this block was pushed across a friction-free floor, say that 3 times fast, for a displacement of 5 meters to the right. 5 meters to the right. Okay, so the applied force and the displacement are in the same exact angle, the same direction, the whole 9 yards. So actually cosine theta is just going to be 1 because the cosine of 0 degrees is 1. So this is actually a pretty easy problem. 10 times 5, the work is 50, and the units of work are the joule. Okay, so 50 joules of work would be required to move this box across a friction-free floor. We have another example problem where we kind of add a new piece here. Basically, Ben carries a 200 Newton suitcase up 3 flights of stairs. Okay, so I'm far from a good drawer, but like these are some stairs, and there's like 3 flights. Okay, and this suitcase must get up these 3 flights of stairs, and the total height, the total displacement here is 10 meters. Okay, that's what it tells us from the problem, 10 meters. Once he gets to the top, okay, and I'm going to kind of do like 2 pictures here. Once he gets to the top, here's the top, he pushes this suitcase with a horizontal force of 50 newtons at a constant speed of 0.5 meters per second for a horizontal distance of 35 meters. Okay, so this thing moves 35 meters. Okay, how much work does Ben do on a suitcase during the entire motion? All right. So I'm gonna put 200 newtons there just to add that in. let's take, because basically this is 2 problems, right? So we're gonna calculate the work here, and then we're gonna calculate the work done here. Okay, so we're taking on 2 problems here. Let's do the stair piece first. Okay, remember, work equals force times distance times the cosine of theta. Okay, so what is the force here? Well, the force of this suitcase is 200 newtons, and that's being provided by gravity, right? The force of gravity is pulling it down by 200 newtons, so Ben must be balancing that force out. So the force is 200 newtons. How far does Ben have to go in total? Now, I realize these stairs aren't exactly vertically straight up. That's not really important. The total displacement from the bottom to the top is 10 meters. And so that is the displacement piece, 10 meters, times the cosine of theta. Now the force is going to be going straight up. You're going to have to apply a force straight up to move this suitcase that direction. And the displacement is also straight up. So notice the displacement and the force are in the same direction. So the cosine of 0 degrees is 1. So 200 times 10 times 1 is 2,000 joules. Okay, that's how much work is required to do this portion of the problem. Now let's take a look at this piece over here, where basically he's moving a suitcase to the right with a force of 50 newtons and a displacement of 35 meters. Again, work equals force times distance times cosine theta. The force applied is 50 newtons times a distance of 35 meters, and the force and the distance are in the same direction, and so it'd be, again, cosine of 0 is 1. Okay, so 50 times 35 is, if you do that calculator work, 1750 joules, or 1,750 joules. Okay, now we want to know how much work does Ben do in total. So basically, I need to add up 2,000 plus 1750, and if you do that math, you have a total amount of work of 3,750 joules. Ben must be tired. He will probably need to take a nap. That actually takes care of this video. I will see you guys next time.